Now I have the pleasure to introduce our second speaker, Landry Soh. He holds a PhD degree in ore geology from China University of Mining and Technology. Between 2010 and 2015, he worked as an exploration geologist at Keystone Resources in iron ore and gold projects in southern Cameroon. Currently work at the School of Geoscience and Infophysics of Central South University in Changsha, China. And the focus of his research is understanding the origin, age, and the positional environment of iron formations and related rocks hosted in the Congo Craton. And is this topic that Landry will present for us today. So Landry, yes.
Thank you, Filipa, for this presentation, and I thank also Ore Deposit Hub for providing this opportunity to present our ongoing research on iron formation of the Congo Craton. So I will present you here some few features in summary of this iron formation in a less studied part of the world. So firstly, I want to thank our key collaborators who have initiated this project, Professor Jean-Paul Senti and Sylvestre Ganno. And we have a deep collaboration with Professor John Tarway and Carlos Rosier, and more recently, Professor Juan Lee and Andre Baker. I also want to thank, on behalf of my colleague, the key partner, Mr. Jodin Bunya and Dr. Jibril Kwatab, who give us permission to access to drill core and other mineral exploration companies such as Caminex, Divine Mining, Aluvance, Cameroon Mining Company, Congo Iron, and Sundance Resource. We also thank our working group at University of Yaoundé 1, Douala, Boya, Chang, and University des Sciences et Techniques de Moscou in Gabon. We have also other collaborators in Brazil, Central Africa, China, Congo, Democratic Republic of Congo, Gabon, India, Namibia, everything. And all these achievements would not be possible without the fund from Chinese Scholarship Council, China University of Mining Technology, and Central South University. So let's go to the main part of our topic, which will be follow this outline. Here we have a special distribution of the iron formation. As you can see, we have it through all the continent with the various deposit size. The huge are in Brazil here, South Africa, Australia, India, Russia, Canada, and USA. All these deposits are age of Archean to Neoproterozoic. We have here the Central Africa region where we have some Mesoarchean to early Proterozoic BF. So why do we study the iron formation? The main reason is that they are the source of iron ore, as they also provide significant clues for understanding the evolution of Earth throughout the Precambrian times. So the main feature of this iron formation as follows. The basic definition of iron formation are chemical sedimentary rock containing about 50% of iron with or not chert layer. We have a classification based on the texture. Here we have BIF based on the alternating of silica and iron layer. We also have here a classification of the granular iron formation, GIF. We also have another classification based on the mineralogy, oxide, carbonate, and silicate facies. Okay, so I was talking about the classification of the iron formation. We have another classification based on the depositional environment, where we have algoma type, like superior, and rapitan type. And we have here a classification, depositional environment of the lake superior in passive margin, and the algoma mainly in volcanic arc. For the rapitan, we have mostly found in grabens. We should know that the iron and silica in iron formation the origin of iron and silica in iron formation can be explained by hydrothermal alteration of oceanic crust, or from continental source, or from a mixture of sea hydrothermal fluid and weathering of continental crust. So we should remind also that the iron formation can be metamorphosed from low grade to high grade with various mineral composition, as you can see in this table. So for the iron ore who are hosted in the iron formation. We can have a soft, friable ore or a hard ore. Here we have some two types of iron ore in an Indian deposit, and the major mineral component of this iron can be oxide, carbonate, silicate. The origin of the iron can be explained by either hydrothermal fluid or ancient supersion weathering process or supersion modified hydrothermal fluid. We'll not go more in deep in this detailed review of the iron formation, and I suggest you to get more detail in this selected review paper. Let's go to the main topic of this talk. So here we have a Central Africa region where we have a cratonic basement that we found in Equatorial Guinea, Gabon, Republic of Congo, and Cameroon. Generally, we have some beef hosted iron deposit in this region. Some of these iron deposits have a mineral reserve estimation that are available to mostly exploration, and not of all these deposits have mineral reservation that have been available. So we can think almost that this region is an emerging iron belt, even there is no mining activity right now. And we should know that there are few data that are available from the literature. But here we will present you some few characteristics of some deposits that have recently studied from from the west to the east. So here we have the cratonic basement in Cameroon, represented by the Ntem complex, was generally divided in Paleopathosic Nyong group and Archean Ntem group and Paleopathosic Aina. Usually, the researcher in the literature consider the Aina and the Ntem group as one unit. So for this presentation, we'll also consider the same thing. So let's talk about the iron deposit in the Nyong group. We have the Ngwab iron deposit where we can find hard massive magnetite in the south part, and in the north part of this deposit we generally have some soft hematite, as you can see here, and also in the west part. Here we have some hard hematite, hard massive magnetite, sorry. So for the petrography of this deposit, we usually have amphibole BF and amphibole parite BF associated with various types of gneiss, schist, quartzite, and dolerite seed that had been intercepted during drilling program. Recently, we also provide some isotope data of this of the iron formation for this deposit. You should highlight that are the first detailed isotope of iron formation in the Congo Craton. From the oxygen isotope of magnetite and quartz, we have estimated the temperature of metamorphism, which could be around 350 degrees Celsius up to 600 degrees Celsius, as you can see it here. And the isotope in data of this iron formation provided also an information of the contribution of seawater and low temperature hydrothermal fluid for the deposition of this BF, which had been confirmed by the geochemical feature of this bit with the plot of the BF close to the seawater and the low temperature hydrothermal fluid. Also, another feature of this iron formation is the low to high content of alumina and titan, and also some trace element like zirconium, carbonate, which suggests a chemical precipitation with an input of detritigous material. So here we also have some chemical feature where we do not find cerium anomaly for the Ngwab BF, and this indicates us some suboxic to relative anoxic seawater for the deposition of this BF. We also have the plot of the rare element, rare element normalized to the past, which show us a contribution of low temperature hydrothermal fluid here and some seawater. So in general, we can also have the age of this iron formation that we got from the zircon extracted from the BF, and these zircon have been dated by LRC-PMS. Here we have Concordia, where we have tested at 2,422 million years, another intercept here at 2,089 million years. The first age has been interpreted as the maximum depositional age of the BF, whereas the second intercept is interpreted as the age of the metamorphosis of this BF. So in conclusion, we have the main feature of this deposit where we do not have the iron ore source. We know we have the soft and hard iron ore, and we also have oxide and silicate features with the main iron as manita, hematite, or martite, and goethite. The rock associated are generally gneiss, schist, quartzite, and dorite. And from the geochemistry of the rock associated with the BF, we estimated that the depositional environment are continental shelf to deep sea water, and the maximum depositional age are around 2,400 million years. We can have more detail on this iron deposit and beef hosted iron and beef and associated rock in these two papers. So let's talk about the other deposit in this Nyong group. We have here the Zambia and Guapo and the Zambi and Kwambo iron deposit, where we generally have beef associated with mafic granulite, gneiss, epidosit, and schist. Here, the geochemical data of the BF show us a contribution of low temperature hydrothermal fluid, as you can see the plot here, with some seawater contribution. The positive serum anomaly that we found, the negative serum anomaly that we found for this BF indicated an oxidized shallow seawater. Other characteristic as the lighter element depletion relative to high element show us the same condition for the seawater. Generally, the beef are associated with metasediment, as we see here, some garnet gneiss, and also some metavolcanic rock. And the plot of this metasediment and metavolcanic show us an environment which is close to the Island arc environment, as you can see here. So, in conclusion, for this deposit, which do not have the iron ore source estimated right now, we have soft and hard iron in this for those deposits with magnetite, hematite, martite, and the rock association as follow. Recent work show us an metamorphosis of the BF and rock associated close to 2,078 million years and a maximum depositional age at 2,466 million years. More detail can be found on those published paper. So we have another iron formation in this Nyong, the Pap Atok Boga and Kelebichuka iron formation with a close association of BF and garnet gneiss. We also have here some beef in the Kelebichuka, where we got zircon from the BF, which have been dated by LRC-PMS, and we have an intercept at about 2,000 and 2003 and 33 million here that is interpreted as the metamorphosis of those BF and the rock associated. The geochemistry of the BF show us a close similarity with other BF in the Nyong, most similar also with the Ntem group, but we think that from the silica and iron content of the BF have been precipitated with a mixture of seawater and low to high temperature hydrothermal fluid, with also a contribution of detrital material. Here we have some metasediment and metavolcanic rock that have been associated with the Kelebichoka iron formation, and the plot of this the plot of those samples show us also an environment close to arc volcanic environment. So in summary, we do not have iron ore source for those iron formation, and not yet a deposit has been evaluated for this location. We have the major iron, which is magnetite, and the rock associated are gneiss and metatonalite. So with a comparison with previous work, we estimated that the maximum depositional age could be close to 2,400 million years, with a metamorphosis around 2,050 million years. More detail can be found on this published paper. Let's go to a less known deposit in this Nyong group is the mammal iron ore deposit, who have been early mentioned by Morris et al. 1986. Recently, Tesson et al. 2020 show us that the iron grade in this deposit are medium. So we do not know the depositional environment, and we estimate that the depositional age could be Paleoproterozoic compared to previous work and previous literature. So let's move to the Ntem group, where we have the good iron ore deposit with various BF like magnetite, granite, biotite, BF, or the BF, and the major ore in this iron deposit are hematite iron ore. The BF are generally associated with various types of gneiss, and we have here some peroxide gneiss. So the geochemistry of those BF show us that we have some low content of aluminum high content of aluminum for magnetite BF and low content for garnet BF, with the similarity with the titan content. And this shows us that the magnetite can be assumed as pure BF, whereas the garnet BF as a contaminated BF. The geochemistry of this BF shows us that we have a contribution of seawater and hydrothermal fluid, similar here in this plot, where we have some where we have some contribution of hydrothermal fluid. For the depositional age of this iron formation, we do not have a clear age, but we have the wall rock late dating will show us 2006 million year, about 2006 million year, who has been interpreted as the metamorphic age of this iron formation. So with the previous literature, the previous work as Morizot et al. 1986, we suppose that the depositional age could be Mesoarchean, whereas the granulite facies of the BF and the rock could be is about 2006, 79 million years. We could have also better detail of this iron ore deposit in this published paper. So we move to two other iron ore deposit in the Ntem group. We have the Bicula and Meomesi BF, where we have generally BF associated with cyanide. On BF also could be associated with cyanokite and high potassium granite. The medium grade of the BF of Meomesi have been revealed by this diagram, as you can see the plot here, medium to high grade, whereas we have an estimated resource of the iron ore in this Bicula from alluvans. We also have the geochemistry of the BF of Bicula, which show the contribution of seawater and low temperature hydrothermal fluid. The absence of true cerium anomaly indicate us a seawater condition that will be suboxic to anoxic. In summary, for this iron ore deposit, we have iron ore source of the Bicula, which is estimated at about 46 million tons. And the major iron ore here are magnetite, kenomagnetic, hematite, and goethite. We have a granulite facies metamorphosis and probably deposition in submarine volcanic environment. And the age is estimated to Mesoarchean. More detail of this iron formation and iron ore deposit could be found in these two published papers. So, more important iron ore deposit here in the Ntem group is the Mbalam iron ore, where we have some BF and the hematite ore here. An estimated depositional age of this Mbalam iron ore BF has been made through the metadacite associated with this BF. The estimated the maximum depositional age of this BF could be around 189 million years. We do not have more detail about this iron ore deposit, but we have some information on this published paper. Generally, we have soft and hard iron ore for this deposit, and the total iron ore resource is estimated at about 259 million tons for the inferred and indicated iron ore source of high-grade hematite, where the intermediate hematite is estimated at 3,924 million tons. Generally, the rock association are metavolcanic, metasediment, metagranitoid, and the granular facies is found for this rock. So we do not have the depositional environment as I said previously, and depositional age estimated at 2,883 million years. So let's move to the Congo, where we have the Ivindo complex basement, and in this basement we have the Nabeba iron ore deposit. We have mostly the banded iron ore formation associated with silicic schist and ultramafic rock and granite and gneiss. So here we have a more detailed map of the deposit. We do not have enough information of this deposit except the recent work of Gatep Epotenuna et al. 2020, where we have a total iron ore resource estimated at 545 million tons for the high-grade hematite and 740 million tons for intermediate hematite. The ore type are generally supergene or hematite-rich, hypogen-rich. Here we have a clear alternation of quartz band and iron oxide band for the BF. From the oxygen isotope of quartz extracted in the BF, we have the recent work estimated that we have different ore fluid shown by this diagram. We have a contribution of magmatic metamorphic fluid with some meteoric water, and the granular facies have been found for this rock association. So in general, we estimate the depositional age of this iron formation in Nabeba as Archean from the work of Melo et al. 1986. We have another iron ore deposit in this Republic of Congo, where named the Batondo iron deposit, with less work. Also, hematite and goethite as the major iron, and the rock associated are generally gneiss with amphibolite and schist associated with BF, which have been metamorphosed up to lower amphibolite facies. The depositional environment is unknown here, also as the depositional age of the rock. You can have some detail in this paper. So we have less information on the iron formation in the Ivindo complex compared to what we have in the Ntem complex. Here we have the Belinga iron ore deposit found in Gabon, with a recent work of Retonda Contra 2020. We found that we have BF associated with gneiss, amphibolite, and metabazite. He found that the major ore mineral are magnetite, hematite in the BF. We have a metamorphism of the rock associated and the BF up to the amphibolite facies. And he found from the geochemistry of the rock associated gneiss, amphibolite, and metambasite that they are deposited maybe in the submarine volcanic environment with a depositional age around 2,900 million years by LRC-PMS. So in summary, what should we know about the iron formation in the Congo Craton? We should know that they are hosted by Mesoarchean to Paleoproterozoic beef sequence that are spatially associated with metasedimentary and metavolcanic rock. In this BF, we also have oxide fractures, which the mineralogy is composed of magnetite or hematite and goethite. And generally, these beef and rock have been metamorphosed during the Ebonian Transammonian orogeny. So we should also know that the beef and the associated rock were deposited from a mixture of seawater, mostly the beef, sorry, not the associated rock, is an error here. The beef were deposited from a mixture of seawater and hydrothermal fluid with a contribution of crustal material in continental passive margin or in submarine volcanic environment. In the Congo Craton, the most important iron ore deposits are the Balam, Nabeba, and Kout deposits. So, next challenge on us is to get detailed lithostratigraphy of the beef-hosted iron ore deposit and the genetic model of the beef and iron ore. Age and of the host rock and how ore should be also known, and the correlation between the iron ore deposit from the Congo Craton with those of the South Francisco Craton in the predrift of the reconstruction of the Gondwana, as we can see here in this few map. The most challenging, the most problem and the most challenging challenge fact that we have is the forest, which cover generally the outcrop in this area. So it's very challenging to work in this area. Thank you for your attention, and you can contact us for any question if you want with this address. Thank you.
Okay, thank you very much, Landry. It's really nice review about these iron deposits in the Congo Craton. If you want, Sylvestre Ganno, you can join us for the discussion. But I have the first quick question, if I can.
Okay.
Is there any relation between the metamorphism rate and the amount of iron ore?
Thank you for this question. Okay. Yeah. Okay. You can continue. Okay.
No, because I was checking every slide that you show the metamorphic rate and the resources. So might have some relation depending on that.
Okay. Right now, we do not make a deep work on the iron ore. Mostly the work have been done on the iron formation. So we could not directly I cannot directly answer about the relation between the metamorphosis grade and the iron ore content in this BF. So I'm sorry that I cannot give you a satisfaction because we do not do work on the iron ore since now, mostly on the iron formation, not on the iron ore. So we hope to have more information on the iron ore, then we can find out how the metamorphosis influence the iron ore content in this BF.
Okay, thank you.
You're welcome.
Landry, we have a question from Phil Smith Lusolo. If you like, you can unmute yourself. If not, I can ask it on your name.
My question is, how did he determine the type of the iron deposit? I don't know if you used the European anomaly or what. Please, can you explain me how did you determine the type of deposit?
Okay, thank you for the question. Yeah, thank you for the question. So the type of the deposit have been determined by the European anomaly as well as also the Cerium anomaly. Usually we have previous work who have proposed us a range for the European anomaly. So we find out that the European anomaly for the most of the iron formation in the Nyong group are lower than 1.8. The European bar dot, sorry, the European star is I don't know if I can write it for you in the chat.
That's fine.
It will be more clear.
Okay.
So
I
there's a
think I'll get
European anomaly that we use exactly to compare with our value, and then we indicate that from this European ratio we have classified that our beef are lake superior or algoma superior. But beside this European ratio, we also have the rock association. We also is characteristic of any type that we have. So the depositional environment is not only from the geochemistry, but it's also from the petrography, the rock association for each BF. I hope that I answer your question.
Okay, that's good.
Thank you.
Okay, we have another question from Martiala Dingra. Do you want to unmute yourself?
Hello.
Hello.
Yes. Bonsoir, Landry.
Bonsoir.
Good evening. Thank you for your talk. And I think that my first question, you give an answer because it was about the metamorphism, the role of the metamorphism in the setting of iron ore deposit. Because when you show all the slide, we can notice that we start from amphibolite facies to going to granulite facies. So the
Exactly.
mineralogy change every time. So I want to understand if most of the time the banded iron formation is what is the role of a metamorphosis in the setting of this mineralogy. And also, but I think that it's always your perspective. You say that you have to define a detailed lithostratigraphy. I don't know if you have a little idea or the lithostratigraphy of the iron deposit in your area of study. Thank you.
Thank you for the question. Thank you. So concerning the mineralogy of the let's say the mineral composition that define if we have a low grade metamorphosis or a high grade metamorphosis. Generally, for the low grade metamorphosis of the iron formation, we have mineral like cumetonite and some amphibole like cumetonite, and also the sericite, typically which define the low grade in the BF. For the high grade, you have some pyroxene. So we didn't have a clear classification of the type of pyroxene, and we hope to do that in future work. So from this main mineral, we decide whether we have a low grade or a high grade metamorphosis of the BF. But specifically for the Nyong group, we also get information from the isotope, the oxygen isotope of the quartz and magnetite. We provide information about the temperature of metamorphosis, and this temperature correspond for the low-grade metamorphosis. It's true that we should do more work on for the isotopy analysis for other deposit to get more information about this specific type of for the grade of the metamorphosis. So for the second question, for according to the drilling that we have, the drill core that we have, we think that we can propose this stratigraphy for the iron formation in the Nyong group, which generally have in the bottom of the sequence. Generally we have quartzite, gneiss alternating with BF, then schist, BF, and gneiss. But in the Ntem group, we mostly have some granite in the basement, alternating with gneiss, schist, and BF. So it's more different, the stratigraphy in the Ntem group with those that with the iron deposit that we have in the Nyong group. So that's the main information. In our future work, we want to make some correlation with representing diamond drill hole between the Nyong group and the Ntem group.
Okay, maybe also the folding is playing a key role in the changing, because you say
Of
that
course,
in the
of
yes,
course, we
so
have some
maybe you have
folding in that area.
yes, so you have maybe to think about this structural aspect of
Exactly,
the place. Thank you very much.
exactly. Thank you for the suggestion.
Okay, we have a question from Aicha Hisu. If you could ask it, that would be amazing because my French is not good. So
Okay, I see. I read the question now and
okay,
I
or maybe you can
understand.
read
Okay.
it out loud, Landry, so other people can hear it also.
Okay, the question from Aïssa Issou is intéressant. Quelle est la teneur primaire géologique, même économique, estimée rentable pour planifier la recherche? So she's asking the iron ore content to organize any research in this area. For the answer of Aisha, I will start with English if she for other speaker. So I think that there's no iron ore content would make us to decide to work. I guess that you're asking for researcher scientists, not the maybe the industry. But if it's for the industry, I cannot answer because I didn't work so much in deep to know why they should continue to search in this or other area. But the scientists, we do not get really a real iron ore consent to decide whether we work on this iron ore deposit or not. The main reason who make us to decide to work is that for the iron ore formation soil in the Congo Craton, there are less information, less data compared to other areas in the world, like in Brazil or South Africa, if we just take those examples. So I hope that I have answered your question. So specifically for French speaker, I will say this. Considérant la teneur rentable qui permettrait de planifier la recherche, il n'a pas été décidé pour ceux qui sont du côté de l'académie d'aller vers une teneur particulière, mais c'était beaucoup plus dans le cadre d'améliorer les connaissances sur les formations ferrifères en Afrique centrale. Par contre, pour ce qui est de l'industrie, je ne pourrais pas vous dire, puisqu'il y a différentes compagnies qui exercent dans la zone, pour quelles raisons elles auraient planifié à continuer la recherche dans un secteur et pas dans un autre. Et j'espère que j'aurai répondu à la question d'Aïcha ici. Merci. Thank you. Is it okay?
Okay. Yes, we have, thank you so much. And thank you for the French and English answer. We have another question from Makugni Ngbo. I'm sorry for my pronunciation. If you want to ask it out loud, if not, I can ask it. Asking, please, what is the difference between hard and soft ore?
What's the difference between hard
and hard ore?
Okay. Thank you for the question. I guess that you have missed the detail that I show for the soft and the hard ore in the first slide of the presentation. The most difference is that the soft are easily friable, so it can be easily grounded and transformed for direct shipping, whereas the hard is massive and need more metallurgic work for extracting the iron iron ore from the other mineral. So it could be from the structure, not the structure, but the physical characteristic of the iron, which is mainly associated with other mineral when it's the hard, and from the soft when it's there's few other minerals between which are associated with the iron. So soft is friable, hard is massive.
Okay, thank you. Just survive another question. We can read this one. Is the difference between the hard and soft ore controlled by the weathering?
Yeah, it's possible that there is a difference between the hard and soft ore, which has been influenced by the weathering. So usually in this part of, let's say, what I know in my best knowledge for the Nyong group, usually we have the hard ore, which is covered by other rocks, and it's not easy for this iron formation to be directly weathered by let's say the water or other factor. So it makes that we have mostly the hard in deep, and whereas in the Ntem group we have mostly the soft ore, which is on the top of the sequence and which has been mostly influenced by the water. And I think that for the hard and soft ore, we have some influence of the weathering will determine whether it's very hard or not, or soft.
Okay, thank you, Landry. I don't see any more questions, so I would like to thank you again for this very informative talk.